All right, so this is the Math 30-1 Transformations Lesson 1, Horizontal and Vertical Translations. And we're going to do some of this stuff here, but I'm also going to use, I'm going to use Desmos, a graphing program, to demonstrate some of the things instead of the experiment. So I'd love it if you all did the experiment pieces, so just pause the video and do the experiment when we get there. So here's the first example of this. What you're supposed to do is apply this formula to solve for the different values. And then make a table of values and graph them. I'm going to do this moderately here, so I'll show you what it looks like. Negative 3 is my x, and I have x squared equals y minus 3. So this would become negative 3 squared, y minus 3. That's 9. If I add 3, I get y equals 12. So that should be 12, though. That's how we do this. Turns out, well, here, pause the video, fill in the table, graph the things, and in about 10-ish seconds, you'll see the completed thing. And we're back. Look, just like you saw, the blue one moved up, the green one moved down. Now, I'm going to actually do this using a fantastic website called Desmos. This is the best graphing calculator you'll ever use. So I'm just going to go in here, and I've already got Desmos up. And I'm going to introduce a variable to my Desmos equation in just a minute. I'm going to use something called function notation that we did back in Math Pensy. You might not remember it. That's okay. So I'm going to just go f at x equals x squared. Now, y minus k equals f at x. In the previous example, we studied values of k that were 0, or sorry, positive 3 or negative 3. When we put it up to positive 3, you can see that it moved it up. If we go down to, well, and again, I've made this negative, so it's kind of backwards. This would be what we saw positive 3, y plus 3, because what I have here is y minus negative 3. Let's actually switch that. Make it look exactly like it looked there. Okay, so if y is negative 3, it moves up. If y is positive 3, it moves down. Okay? Kind of the opposite of what we expect it to do. And that's okay. Back to here. So when we replaced y with y minus 3, the effect that it had was moved up 3. When we replaced it by y plus 3, it moved down 3. Here's why this is. What we're going to do is we're going to call this original graph y old equals x old squared. My new graph, I've replaced the y with y minus 3. So I now have y minus 3 equals x squared. This is my new graph, so I'm going to put little n's on my variables there. Old's for old and n's for new. So what I now have is y new minus 3 was replaced by y old. Or put another way, if I rearrange this and add 3 to both sides, y new equals my old y plus 3. So whatever the old coordinate was, add 3 to it, and there's your new coordinate. That's why it moved up. when we've replaced it with y n plus 3, right? Then what we had is y new equals y old minus 3, which moved down from the original graph. All right. We are now going to demonstrate this. If you just type these in your graphing calculator, there's that one. There's that one. Oh, I'm actually doing it wrong. Here's that. And there's that. The reason that this moved up is that it could be written as y minus 2. So that's what the replacement did. The y minus 2 replacement moved up 2. The y plus 3 replacement moved down 3. So based on this graph, if we have it like this, this moves it up k units. And similarly, this moves up k units. So we call this a vertical translation of k units. And if k is positive, the graph moves up. If k is negative, the graph moves down. And now, again, if I change this back to a y minus k here, and then I shuffle this thing around, negative k down, positive k up, negative k down, positive k up. Now, you have to subtract the positive k to make that make sense, but that's what we do. Okay, back to here. Next thing to look at is what happens with the h value. If you really want, you can fill out the chart. I really don't want to. So instead, I'm just going to demonstrate this in Desmos. Minus h. Actually, let's go plus h to start. And then I need to include my newfangled h term. Oh, equals h. That's supposed to be minus. Oh no, plus. Equals again. There we go. Mr. McManus can, in fact, work the keyboard. Probably. So if I have like plus 5, it moved it left 5. If I have it negative 5, so like x minus 5, it moved it to the right 5. Again, somewhat backwards of what we would expect. So I'm going to change that to a minus there, minus h, and then we can see the way that it all goes down. So if I replace with x minus 3, it's actually going to move it 3 units right. Again, the same logic holds true. This is the new graph. So x old equals x new minus 3. Well, then if I add 3 to both sides, I get x new equals x old plus 3. That's how I know it moved 3 units right. This replacement moves 3 units left. I could do the same thing with the graphing calculator. This is going to go 4 right. This is going to go 2 left. And then I can write this like this, with x minus h. So this is what we call a horizontal translation. Of h units. If h is positive, the graph moves right. And if h is negative, the graph moves left. Now again, remember that subtracting a positive number will look like f at x minus 2, right? So it's not really subtracting, it's subtracting a positive number, which moves it to the right. Okay, so this is what we have now discovered. This is the notes kind of part. Now let's see what happens. So if I replace x with an x plus 2, x old, x new plus 2, it's going to end up moving it 2 left. This would be 8 up. And again, you can just memorize that, or you can pay attention to why it's happening. The why it's happening is that we have x old equals x new plus 2. Well, I don't want to get directions from the new point to the old point. Take the new point, go up 2, and there's the old point. I'd rather rearrange that to give me this. So that's take the old point and subtract 2. That's going to move it 2 units to the left. This is going to be 3 right. This is going to be 4 up. Again, I would do it like this. Y minus 4 equals f at x. And that's going to move it that 4 units. All right. So here I have y minus 1 and x plus 10. That's going to move up 1 unit. Up 1 and left 10. All right, here we have another style of question. The points 2, 3 lies on the graph. State the coordinates of the image after the following transformations. So there's 2 ways of solving this, the algebraic way and then just the understanding what happens here. Y plus 8 means 8 down. So if it was at 2, negative 3, 2, negative 3, somewhere like that, it's going to move 8 units down. It's going to end up at 2, negative 11. Okay, the other way to do it is to go like this. Y new plus 8 equals y old. Then I go y old is negative 3. Y new plus 8 equals negative 3 minus 8 minus 8. Y new equals negative 11. So I can either do it kind of graphically, or I can just do it algebraically and let that piece solve out. What I would like to do in this one is change it a little bit to this. At x minus 7. So what I'm going to do now is I'm going to add, this is going to be 5 up and 7 right. And so I could just do kind of the quick sketch here. 2, negative 3 is going to go up 5. So that's going to be at positive 2. And over there, so it's going to be at 9, 2. Or I can go y new minus 5 equals y old. And x old equals x new minus 7. And then put the values in. So negative 3 is my y. Add 5 to both sides and get positive 2. My x old is 2. Add 7 to both sides and I get 9. There's my answer. Okay. Write the equation. 5 units left, horizontal, that means it has to be a change in the x. So this is going to be x plus 5. 3 units up, this is going to be y minus 3 equals f at x. Now be careful, you might sometimes also see it as y equals f at x plus 3. We get there just by adding 3 to each side of the equation. Both of them are fine. Translation n units right and p units down is going to be y plus p equals f at x minus m. Good. We could also, if we cared to, write this as y equals f at x minus m minus p. Okay. The last thing we can do is they can give us a graph and say to do the change. So f at x minus 2, this is going to move it to right. So I'm going to move that to there, this to here, this to here, this to here, this to here, that to there, and then connect my dots. Done and done. There is actually kind of a nice way of letting your calculator do this, but it takes a little bit of time. It's usually easier just to do it by hand. I will record that other video at some point to put it up here if you'd like to see it. Ask Mr. McManus about it or search it up. We'll find it for you. Okay. This one here is going to go 2 down and 3 left. So 2 down and 3 left is going to put it there. 2 down, 3 left there. 2 down, 3 left there. 2 down, 3 left there. And okay, connect yon dots. That's where that one's going to go. Now, there's 2 different notations that they're going to use in the course here. Mapping notation and replacement notation. I love this understanding mapping notation and replacement notation. There are all sorts of tricky things that they will do that will kind of sneak you through. And if you're really strong with mapping notation and replacement notation, then life gets really, really easy. So here's this example. This would be up 2 and right 3. The replacements are that. Replacement notation is when I give you the old value in terms of the new value. So x old is the thing that's isolated, minus h, for example. Or y old equals y new minus k. We can sometimes also see what we call mapping notation. So we decided this would be up 2 and right 3. Where mapping notation comes from is you start with some coordinate, and we're going to call that coordinate, that point, x comma y. So those are the original coordinates. I'm also just going to call these x old and y old. But what I'm going to do now is I'm going to add 2 to my y. So it's going to be y old plus 2. And it would be x old plus 3. And I'm going to put that in coordinates. And this is what we call the mapping notation. This point mapped to this new point. I can still do this the same way I did before with my mapping notation, my new and my old. This is my new point. This is my new y value. So I can now write x new equals x old plus 3. So in mapping notation, it's the new value as a function of the old, or the x new that is an isolated part. And they're sneaky because they look very, very similar. So this is mapping notation, right? And this is, actually, let me redo that here a little bit. That's the mapping notation, this top thing. And this is the replacement notation of this thing. Again, as long as you keep straight which is the old point and which is the new point, you're in great shape. Okay, So state the coordinates of the image of the point -3, 5 under the translation described by this. So if they've given me this is the old point, x old, y old, and this is that value, so this is also my x old and also my y old. This is my new point, so it's x new, y new. So x old minus 7 equals x new. Y old plus 4 equals y new. So they've given me the old point. What are the coordinates of the image? The old point, this is x old, y old. So I'm just going to put this in like that. So my new x value is -10. So it's going to be -10, 9. This is, again, mapping notation, but now they want the equation. I can't put mapping notation into my equation. I can only put replacement notation into my equation. So x old, y old is x new, y new. So I can now write x new equals x old minus 6, and y new equals y old plus 1. I'm going to isolate for my old point to get it back into replacement notation. So I'm leaving off my new y. And x old equals x new plus 6. So now if I have y equals f at x, I can now, and sorry, those are my old points, I can now do my replacements. I'm going to replace this with that. Here we go. X old was replaced by x new plus 6, and y old gets replaced by y new minus 1. So y old got replaced by y new minus 1. So this is the equation that would cause that change to be mapped like that. All right, hopefully that helps with the understanding of replacement versus mapping notation. We're going to continue using that same vocabulary for the rest of the lessons in the unit, and we'll really build a strong understanding of these transformations.